When working with empirical data, results of experiments, simulations, data obtained from components, tests, or statistical records, researchers and engineers usually face a need to find the law that approximates the relationships between dependent and independent variables. This is where curve-fitting techniques become handy. In general cases, the process of finding a mathematical function that fits behavior in data is quite straightforward, and there are numerous tools that help to find the solution. Some of these tools offer only graphical outputs, plots with fitted curves, without providing access to the underlying model. Others provide options to choose between predefined models, which you would have to re-implement manually in your code by typing in formulas and coefficients. More advanced curve-fitting capabilities are available in many proprietary software packages and interactive toolboxes. However, the accessibility of the obtained models is limited. And there is always an option to use a pure programmable approach, leveraging open-source libraries for curve fitting, which on one hand allows for greater control over model parameters and enables reusability, but on the other hand comes at the cost of time and ease of use. Ultimately, choosing a curve-fitting approach often means making trade-offs between accuracy, ease of use, cost, and reusability of models. This is where SplineCloud stands out by addressing every one of the listed aspects. With SplineCloud Free Plan, you can fit curves using parametric splines, a universal method that provides the highest possible flexibility and precision. Fine-tune your curves interactively with real-time feedback. Extract fits directly from plots and graphs, share your models, and reuse them in code as regular functions. In this step-by-step guide, I'll walk you through all these features and show you how to build, share, and reuse fitted regression models in code using SplineCloud. So, let's jump right in. First, start by creating a new data repository on SplineCloud. Of course, if you haven't already created one. Then click Upload File to add your data file. It can be a text file, like CSV, a spreadsheet, or even an image containing plots. Once your file is uploaded, click on it, and a default dataset will be displayed. You can adjust data loading options using a toolbox on the right. It is a good practice to give datasets proper names to simplify search and navigation. Click on the Fit Curve button. The default data relation object will be created and associated with the dataset if there are no relations created before. Select the proper columns you want to use for the X and Y axes from the drop-downs. Now, basically all you need to do is click on Add Curve on the Curves toolbox. When you add a default curve, SplineCloud automatically fits it to your data using the default settings, which produces nice results in the majority of cases. However, you have lots of freedom to control the fitting parameters to achieve higher accuracy or smoother approximations. SplineCloud provides 3 automatic fitting methods that you can choose from. Least squares splines is a great general-purpose fitting method that minimizes the sum of squared differences between the spline and the data points. By choosing this method, you can adjust the spline order and the number of knots to balance accuracy and smoothness. More knots means more flexibility. Fewer knots means smoother curves. The least squares method allows for controlled approximation rather than exact interpolation, making it ideal for noisy or irregular data. However, this method tends to overfitting when data exhibits a non-monotonous dependency. Use interpolating splines if you need the curve to pass exactly through every data point. This method is best suited for clean, precise data where an exact fit is more important than smoothing. But in real-life problems, this rarely happens. Experimental data usually contains outliers, noise, and deviations. This is when you would like to use smoothing splines to obtain smooth approximations and reflect main trends in data. In addition to the spline order, you can tune the smoothing factor that controls spline smoothness. This method is less subject to overfitting, meaning you can use smoothing splines even when fitting oscillating relations. When selecting fitting parameters, you can always refer to the fit accuracy hint on the toolbox, which recalculates the root mean squared error after each adjustment. If some data points are known to be more important than others, You can increase their weights by right-clicking on them and selecting the W+ option. This will force the least squares and smoothing algorithms to fit closer to the points with higher weight. You can also reduce and reset weights of data points from their context menu. A few words about widget controls. Use the scroll to zoom in and out. You can also drag the canvas to place the region of interest in the focus. To restore the view, click on the button with the stretching rectangle symbol at the top right corner above the widget. If the data you are fitting was extracted from the plot, there will be toggles with image symbols next to the Restore View button. Use these toggles to display the plot on the background. This is quite helpful when you try to maximize the similarity with the original curve. Once you have selected the fitting parameters that work best for your data, you can reuse curves in your code as regular functions. For Python and MATLAB users, SplineCloud provides client libraries to simplify that process. If you are using Python, you can install the client from the Python package index. Use the command pip install splinecloud-sciy. Now you can import splinecloud-sciy library and use its method loadSpline to reconstruct spline object in your code. For this, simply copy the curve ID from the curves toolbox on SplineCloud and insert it as an argument to the loadSpline method. To evaluate spline values, use the eval method of the spline object. Now, you can use your spline in further analysis or optimization without the need to recreate regression models, typing in formulas and coefficients, or refitting models to data on each run of your code. If you wish to load the underlying data, use loadData method of the spline object. You can also evaluate the fit tolerance of the spline by calling fitAccuracy method. For MATLAB users, there is a client script that does almost the same. You can download it from the MATLAB File Exchange portal, link in the description. So, let's get back to SplineCloud to take a look at the advanced curve fitting options. In some cases, relations in data are quite complex. Some areas may remain underfitted, and reduction of smoothness is not desirable. This is when you may want to switch to the fine-tuning mode and adjust the curve shape manually. This is a powerful method that you can use to achieve the best compromise between smoothness and accuracy. To learn more about this mode, watch the next video in this series. You can add more curves to compare them and select the best fitting options. If needed, you can rename curves. But more important is to give proper names to data relations. This will help you and others in finding relations and understanding what they represent. To share the relation with your colleague, copy the web link to it from the link drop-down menu. Here, you can also copy the relation API link that you may want to use when writing custom automations. To learn more about SplineCloud API, read the API guide. The link is in the description. Alright, I think I have covered all important aspects that will help you in starting your journey into simplified and reusable curve fitting. Drop your questions and suggestions in the comments and subscribe to the SplineCloud channel to be updated. And remember to check the video guide about the fine-tuning mode.